That first homework assignment is due next Tuesday in class, and the textbook is in the bookstore. Have any more of you received your books in the mail? Some of you have. Some of you are still waiting. Well, of course, you're welcome to work together on homework assignments in as much as you can discuss the problem statement and you can talk about the general principles of the problem, but then each solution needs to be independent. You know, you shouldn't be submitting the same exact solution as another student. You shouldn't be working every step of the problem together, because then that robs you of the opportunity for independent effort. So until you get your books, you may need to collaborate a little bit more tightly than once everybody has their own. We're going to continue our discussion of flow resistance with finishing up this example, and then we're going to continue on into textbook chapters 7.4 and 7.5 and talk about different flow types and velocity distribution and how that can be described with some of the shear stress calculations we've done so far. Any questions before we continue with that example? All right, so what we already did was found the slope of the energy grade line, and next we want to find the pressure change over 100 meters of pipe. And one thing to point out is that this pipe is very steeply inclined. A slope of 0.1 meters of vertical rise per 1 meter of horizontal length is a very steep pipe slope. But there's something we need to prove to ourselves, and that is, how does the energy grade line slope vary on the basis of horizontal length versus pipe length? Because obviously the length of this pipe is going to be more than just the horizontal component of its length. And that's especially true for a steeply inclined pipe like this. At the end of this proof, we're going to see that it doesn't vary that much, that the two slopes are pretty close together, so for the rest of the semester we won't even bother to distinguish between the horizontal length and the inclined length. But this is what will make us feel comfortable in doing that. So if it is 0.1, the slope, then we have 100 meters of horizontal length and 10 meters of vertical. And if we want to find what is that angle in there, we can find it by arctangent of 10 over 100, and that gives us an angle of 5.71 degrees. And that's the angle there. In a typical municipal water supply, the slopes would be much less than this, so this is an extreme example. If we find the cosine of that angle, it's 0.9950. And so remember that the definition of the H sub f, the energy loss per unit length of pipe, we can find the slope of the energy grade line divided by the cosine of the angle. And so it was 0.12232 meters per meter divided by 0.9950. And that gives us that we're going to be losing 0.12294 meters of energy for every meter of pipe length that we flow through. And so that's not much different from the slope of the energy grade line. There's a small variation there. So again, what this is this is the head loss per 1 meter of pipe length, whereas the other was for a horizontal meter, not per horizontal meter. So it would be unusual for us to find a case where we need to actively distinguish between the two. That's just an aside. Now let's look at the pressure change over 100 meters of pipe. To do that, we need to apply the energy equation. And of course, the energy equation is the pressure head and the elevation head and the velocity head is equal to the pressure head at 2 plus the elevation head at 2 and the velocity head at 2 plus the energy loss. in this case due to pipe friction. H sub F represents the energy loss. Since this pipe diameter isn't changing, the velocity at 1 is going to equal the velocity at 2. And so we can cancel the velocity head terms out of the equation. Let's say that we're going to set our datum such that the elevation at 1 is 0, and we'll measure elevations from there. So if we have 100 meters of pipe length, then we can find the energy loss by that 100 meters of length times the slope. And that means we're going to lose 12.294 meters of head over a 100-meter length of pipe. That's how much energy loss there's going to be. And so how much of a pressure change will that account for? Well, we'll have P1 minus P2 divided by gamma is equal to Z2 plus H sub F. So the pressure changes based on two things. The pressure changes because the elevation is increasing from 1 to 2, but also the pressure changes because pipe friction is reducing the energy that's available in the water. So these are the two reasons why the pressure is changing between 1 and 2. Well, we can substitute in the Z2 relatively easily. We know that the Z2 will be 10 meters. That's how high it's going to be, 100 meters down the line, because of the slope. The physical slope of the pipe is 0.1. So that gives us Z2. And the H sub F that we've just calculated, that is 12.294 meters of energy. And then we need to multiply that by gamma. So 9810 newtons per meter cubed. Okay. And from that we get the change in pressure. So I guess I have moved the gamma over to the other side. So what we have here is just going to be the pressure change is equal to, it's a little crowded, H sub F. So the delta P is that times gamma. And so the change in pressure is 230 newtons per meter squared. And that accounts for both the energy loss due to pipe friction and the hydrostatic effect that at 2, the pipe is higher in elevation than it was at location 1. So you have a homework problem that gives you a shear stress and asks you to do similar things to this. Asks you to calculate the pressure loss, asks you to find the slope of the energy grade line, and so on. Yeah. The definition of the slope, where it says S naught is 0.1 meters per meter, it's talking about 0.1 meters of vertical per 1 meter horizontal. And so that's just by definition, that's how the slope of the pipe is defined. And so if we know that it's 0.1 to 1, then that also tells us it's 10 meters for every 100 meters of horizontal pipe length. Does that answer your question? Okay. Other questions? You've seen piezometers before. You saw piezometers in the experiment where we were having the pipe contract. It was the Bernoulli's experiment. And you saw the water level decrease at the piezometers that were at the throat of the venturi. And then the water depth increased after the throat expanded again. And of course, the reason why the piezometer depth was decreasing was that in the throat of the pipe, the velocity was higher. And that piezometer was illustrating the effect that when velocity increases, pressure decreases. So what a piezometer is a way of identifying where the hydraulic grade line is. And in this pipe, you can see that the velocity isn't going to change inside of the pipe between the two piezometers that are shown because the diameter is the same in that particular section of pipe. And so the H sub F that's indicated there, which is the difference in elevation between the upstream piezometer and the downstream piezometer, that H sub F is the energy loss that's due to pipe friction. And again, the HGL, you can think of that just as a graph of the potential energy that's in the fluid, the potential energy being its elevation above some datum and the pressure head that's there. The piezometer doesn't measure the effect of the velocity head. But if we reconfigured the piezometer a little bit, we could probably get it to quantify the energy grade line. And we had an illustration back in Chapter 7 of the book from last semester that was distinguishing between what would happen if you had a pipe and the water's flowing through the pipe, and then it had a piezometer like this, and then it had another device where it was going down and intercepting the flow. And in that example, the water rose to a higher level so that there was some difference in elevation. So a piezometer isn't intercepting the velocity of the flow, whereas a pitot tube, which is what we were talking about with airplanes, a way of measuring the energy in a flowing fluid. If the streamline intercepts the opening of a pitot tube, then the water level would rise a little bit higher. But here we're just talking about a piezometer, and so the way that you can find the hydraulic grade line is by connecting the dots between piezometer readings. And so it's the pressure head and the elevation head. Now, you can have a change in the sum of these two terms, and if you have a sloped pipe, then you need to keep track of the change in elevation separately from the change in pressure. And so the change of the sum of those two terms is because of pipe friction. And this right-hand side of the equation is the Darcy-Weisbach equation, which is a way of saying how much the energy is going to be lost due to pipe friction. And of course, it's a function of length and velocity and the diameter of the pipe, and then this magical friction factor F that characterizes how rough the pipe is under certain conditions. And so when we combine those two ideas together, that's where this Darcy-Weisbach equation comes from. And we'll use this a lot. In fact, it's our primary design equation through the closed conduit part of the course. And you remember when you're using water gems, one of the first things you'd do is you'd go into water gems and you'd take it out of the, if it was in the Manning mode or if it was in the Hazen-Williams mode, and you put it into Darcy-Weisbach because this is the more accurate way to measure energy loss. Again, if it's an enclosed pipe, then the slope of the pipe, S naught, can be independent of the slope of the energy grade line. We could have a horizontal pipe where the pipe slope is 0, but still there's going to be a slope to the energy grade line because energy is being lost. And so just to illustrate what I mean, if we put in a piezometer downstream, then the water level isn't going to be as high downstream because energy was lost due to pipe friction. And so here's the HGL, and here's the S sub F. It's the slope of the hydraulic grade line, whereas in this case, if it's a horizontal pipe, you can have any pipe slope you want, and it'll be independent of the slope of the energy grade line. That's not true for an open channel, though. There's something in the book where they rearrange the expression of energy loss and shear stress to come up with a term called shear velocity. We won't use it a lot during the semester, but shear velocity does come up in one or two of the problems, and so I wanted to go through how shear velocity is derived and how you can calculate it. One of the earlier things that we looked at on Tuesday was the relationship between the shear stress, tau, and the other parameters of the flow length in a pipe, and R is the hydraulic radius. And does anybody remember how you can calculate the hydraulic radius? There's two terms that go into it. It's area over perimeter. Pretty close. So that's hydraulic radius. And so when you have a pipe, then you need to look at the shape of the pipe. The shape parameter goes into the hydraulic radius, and the length of the pipe between two sections. You can calculate the energy loss due to pipe friction if you know the shear stress. And you could also know the energy loss due to pipe friction by estimating the friction factor F. And so if you combine those two things together, then what that gives you is a relationship between the friction factor F and the shear stress, the boundary shear stress tau. And so if we rearrange that a little bit further to find in units of meters squared per second squared, if you have the shear stress of a fluid that is flowing from point to point, the shear stress that's being imparted to a fluid from a pipe, and you consider the density of that fluid, then that is the definition of shear velocity squared. And so if you take the square root of those two terms, if you take the square root of the shear stress divided by the density, then that's how you would get, in terms of meters per second, a representation of the force that's being applied to the fluid. So it's a dimensional analysis thing, really, just rearranging the units until a parameter you're interested in is being expressed as a velocity, an equivalent velocity, rather than in terms of a force per unit area, as shear stress is. And so it's a way of accounting for the shape of the conduit, the fluid properties, and expressing the forces that are being applied in terms of a velocity, an equivalent velocity. That's sort of the long and short of what shear velocity is. You can equate shear velocity to the Darcy-Weisbach friction factor F using this formula. And in fact, you'll need to on the homework assignment. You'll need to use this formula for certain flow conditions, just to say, if this is the shear stress we have, then what is the equivalent friction factor F that should come from that? And this is really how they come up with friction factors. Friction factor is an empirical thing. The equations we use to calculate F are empirically based, and so it's through measurement of fluid flow properties and the head loss that's occurring that they come up with the F values. And so it's a process of really long and repetitive experimentation many years ago that came up with the Jane equation and the Colebrook equation we'll learn next week for estimating F. So the thing I've overemphasized so many times is that the slope of the energy grade line for an enclosed pipe is independent of the physical slope of that pipe. The pipe can be horizontal, and you can still have a downward sloping energy grade line. That's not true for an open channel. Now, in an open channel, the slope of the channel is equal to the slope of the energy grade line when you have steady, uniform flow. And we're going to get into that. Before we do, let's consider just the geometry of a trapezoidal channel like this. In the book, the lowercase b is the variable that's assigned to the bottom of the channel. And then usually it'll have side slopes. It's not common, especially in an earthen channel, to have just a rectangular channel where the side walls are vertical, obviously because the soil can't stand up completely vertical. You can maybe have a concrete channel that's rectangular or a rock channel that's rectangular, but oftentimes an earthen channel and even concrete lined ones are sometimes trapezoidal in geometry. In the book, on page 301, is a bunch of really useful formulas based on different shapes. It gives you, for a rectangular channel, trapezoidal, triangular, circular, and so on, the formula you'll need to calculate the area, wetted perimeter, hydraulic radius. All of the geometric parameters you need are on page 301. We'll take a look at a few of them here in an example. For a channel like this, the same flow resistance equations apply. You can relate boundary shear stress to the slope of the energy grade line. That's still valid. The thing that's different here with the hydraulic radius is that the top of the channel, where the water is touching air, is not included in the wetted perimeter. So P sub W stands for wetted perimeter. And in a pipe that's flowing full, the wetted perimeter is just the entire circumference of the pipe. In the case of a trapezoidal channel or a rectangular channel, you don't count where the air and the water are touching. You only include in the wetted perimeter that physical perimeter of the channel that's in contact with the water. So, as I mentioned, if you have steady, uniform flow, so remember, steady flow is where conditions aren't changing over time. That means that the flow rate and the flow velocity now are the same as the flow rate and the flow velocity in the future or in the past. Conditions are steady over time. Uniform flow means that conditions aren't changing with respect to position. And so that means that the depth upstream and the depth downstream are the same. So steady, uniform flow, the channel bed slope, and this is the slope of the channel bed, the bottom of our channel, is going to be equal to the slope of the energy grade line and the slope of the hydraulic grade line. All three of those slopes will be equal to each other for steady, uniform flow. You can see that the HGL, the hydraulic grade line, is equal to the water surface for a stream. And then it's abbreviated here, total energy line, or as we called it back with the other textbook, EGL, energy grade line. They mean the same thing, total energy line or energy grade line, is above the water surface equal to the velocity head, v squared divided by 2g. Okay, so let's take a look at this question. What is R for a trapezoidal channel in terms of the bottom width and the depth y? This is just sort of a getting to know you exercise for trapezoidal geometry. You're going to get really good at solving trapezoidal geometry because we'll have so many problems through the semester where we have to consider flow through a channel that's trapezoidal. So we have some channel and there's water in it. It has a bottom width of b, has a depth of y, and side slopes of 1 to t. And we can find this length, this side length, is the square root of y squared plus t times y squared. That's how we can find that length. And the reason why is that this section over here, the length of that section is t times y. If you have, this triangle is saying for vertical of 1, you have horizontal of t. That's defining the slope of that side slope. And so if our depth is y, then that means that this segment right here is t times y. Okay. All right. Hydraulic radius is area divided by wetted perimeter. Some books, and sometimes just out of habit, I'll say R sub h for hydraulic radius and P sub W for wetted perimeter. If I forget to do that, or if you come across a reference that doesn't, don't be thrown off. It means the same thing. So what's the area of this trapezoid? Area. Why don't you try and figure that out on your paper there? What is the area, the cross-sectional flow area of that trapezoid? I'll give you a minute to think about that. Okay, so obviously you can break it up into pieces, right? you'll have this rectangular piece that is B times Y, and then you've got two triangles, one on either side of the trapezoid. So if you put them together, that's just another rectangle. So it's going to be B times Y plus Y times TY. Okay, in other words, that is BY plus TY squared. That is the area. And the wetted perimeter is going to be B plus two of these side lengths here. So it's going to be B plus 2 times the square root of y squared plus ty squared. And we can simplify that expression a little bit further. We can say it is B plus 2y times the square root of 1 plus t squared. And so the hydraulic radius, in conclusion, will be by plus ty squared divided by b plus 2y square root of 1 plus t squared. Yeah.
Where's the TY at the very end of
This?
I'm talking about drawing. Yeah. How do you
Okay.
determine that?
Because we are given that the slope of this side slope is the vertical component of the slope is 1 and the horizontal component of the slope is t. And so, you know, like maybe we'd have a trapezoid that's like this, really steep slopes. Maybe we'll have a trapezoid that's like this. And just the way that that slope is defined is we call this, we say for every one vertical, there's t horizontal. T is some variable. You know, maybe it'll be a 2-to-1 side slope. That's a pretty common thing, is to have one vertical and two horizontal. So that would be a 2-to-1. In this case, we're just calling that t, and so the depth, for some depth y, if you had the horizontal component t, then the top length there is going to be t times y. So if it was like a 2-to-1, remember I said 2-to-1 is pretty common? So if you have one vertical, then you'll have 2 horizontal. Or if you had 2 as the depth, then you'd have 4 along the top there. So t is just how they choose to define the geometry of the side slope.
And then when you're doing the area, I guess instead of putting 1/2 twice,
I combine it together. Exactly right. Yeah. So there's these two triangles that I consider together as another rectangle. Good questions. Are there others? Yes.
Why do you not include the top of the trapezoid to the front?
It's because the water isn't getting slowed down by its contact with the air. The water is touching the concrete, and the concrete is applying a shear stress to it. But the air sort of moves along with the water. And so it's not a surface that's providing resistance. And so in the wetted perimeter, it's just where the water is in contact with a solid surface. There's a little bit of an effect with wind. I mean, in a velocity distribution, so, you know, water flowing down a stream, here's the bottom of the stream, here's the water, you know, and of course we know from the no-slip condition that the water velocity, the water that's touching the bottom of the stream is actually not moving at all. You remember that video I showed you where they injected a dye at the bottom of a flow channel and the dye sort of just stayed at the bottom of the tank because there's no velocity at the bottom? We can look at that again when we get to it, but a velocity distribution would be very low velocities at the bottom, and it increases, and there'd be just a tiny little bit of a tapering there. So, I mean, there is some resistance, but it's minor enough that we don't include it in the hydraulic radius. The Chezy equation is an empirical way of keeping track of energy losses. This is sort of like the first attempt to come up with a formula engineers could use to say, what's the velocity of water flowing through a pipe? You know, if that's the main question, how fast is water going to go through that pipe channel? The Chezy equation was the first widespread way of calculating that. It was improved upon later by Manning, but there were these roughness values, C values, that were empirically determined through experimentation and observation. And a very rough C value for maybe like a brick-lined pipe would be on the order of 10, and a very smooth pipe would have a higher C value. And the way that works out is obviously if you have a high C value for a smooth pipe, then that's going to increase the velocity for some given slope of the energy grade line. So S sub F is what's driving flow. Like, why does water flow from one place to another? Water flows from a location of high energy towards a location of low energy. And so what drives the water down through a pipe is the energy differential. And so you can think of here, you know, what causes the velocity in the pipe is S sub F, the driving force, and R, of course, is the hydraulic radius, which accounts for the channel geometry. And then the C value is that roughness coefficient that sort of tied it all together. And you can see that the roughness coefficient would have units of length to the 1/2 power per time. One of the improvements that have been made on the Chezy equation is that it turns out that if you take slope to the 1/2 power but hydraulic radius to the 2/3 power, then it fits the data a little bit better. Velocity distribution we've just talked about in an open channel. The velocity distribution is that at the bottom of the channel the velocity is 0 because that is where all of the resistance is being applied. Now, as water moves, the bottom of the channel is pushing on the water. We did a force balance in class on Tuesday, and we looked at all of the forces, the weight of the water, the pressure forces on either side, and also the resistance opposing flow. So here the channel is pushing on the water. As the water flows downstream, the channel is pushing back. Otherwise, it would continue to accelerate. And we know it doesn't do that. It reaches equilibrium. And so the way it reaches equilibrium is that that concrete surface or clay surface or gravel, whatever, is pushing on the water. Here in an enclosed pipe, it's not just at the bottom, but it's all around the edge of the pipe that force is being applied. And so if we're looking at a cross-section here, we've looked at this principle before, that the velocities will be the highest at the center of the pipe, which is further away from the pipe edges. And so here at one edge of the pipe, the velocities are going to be 0. And then up at this pipe diameter, whatever the diameter might be, again the velocities are low because that's another surface that the forces are being applied from. Logarithmic versus parabolic distribution relates to the velocity of flow through the pipe. And if the flow is laminar, then the shape of the velocity distribution will approximate a parabolic shape. And that's those rare cases when the Reynolds number is less than 2,000. But then when we get above 4,000 for the Reynolds number, there's going to be a lot of random behavior, and there won't be as a well-defined cone at the center of the pipe of velocity. It'll be more flat. And there'll still be low velocities at the edge of the pipe, but that's the effect of the location that the forces are being applied at. This is a little bit more, I don't know, a little bit harder to visualize what's going on in the water. So we're going to spend a few minutes talking about boundary layer thickness. This is at the edge of the pipe. So we were just talking about where the velocity is high and where the velocity is low in the pipe. The velocity is fast in the center of the pipe. The velocity is slow at the pipe edge. Now, what does that do to the Reynolds number? Remember, Reynolds number is a function of the velocity, the diameter, and the kinematic viscosity of the fluid. That's how we can calculate Reynolds number. Now, there is an average velocity for the cross-section of a pipe, but what we saw in this figure is that whether it's a logarithmic velocity profile because of turbulent flow, or if it's a parabolic velocity distribution because of laminar flow, it doesn't matter, but the velocity is not the same everywhere. You know, the velocity down here close to the pipe wall is small, and the velocity further away from that is fast. And so what that means is that there's a different Reynolds number at different locations in the pipe. Even when you have turbulent flow in a pipe, you know, in general conditions are turbulent. If you get close enough to the pipe wall, there's a zone where conditions are laminar because the velocity is really slow close to the pipe wall. And so what this is going to be representing, the next couple of slides that we're going to look at, is how thick is that zone where there's a laminar sublayer underneath the turbulent flow that's above it. So this is showing if you get far away from some pipe wall, so that this bottom horizontal axis, you can think of this line as the pipe wall itself. Now, the thickness of the boundary layer varies as a function of flow conditions. And this line is representing shear stress. And the shear stress, when you have turbulent flow, shear stress is reaching further out into the water. When you have turbulent flow, it's because the velocity is fast. You know, high velocities give turbulent flow. And obviously, if you have high velocities, there's going to be more resistance to flow. And that resistance is being felt further into the flow. And so that's why this line is higher for sub T, which means turbulent, than it is for sub L, which means laminar. If conditions are laminar, then the shear stress is lower. But what happens to the thickness of this boundary layer is what we're interested in. How does flow velocity change the thickness of that boundary layer? Now, a boundary layer, sometimes we call it a laminar sublayer, has its thickness varying based on flow conditions and also based on the roughness of the surface itself. So it's partially affected by what kind of a pipe material you have. So above the boundary layer, conditions are turbulent, but it's sort of like a cushion. It's a cushion beneath the turbulence where conditions are very calm. Think about a roaring river. If the fish goes down to the bottom of the roaring river, it can sort of hide out behind a rock. And the velocity won't be high behind that rock at the bottom of the river. And the flow will be quiescent there. And what we're going to look at is the thickness of the boundary layer in fast flow velocity versus slow velocity. If you have slow-moving flow, then that boundary layer will be much thicker than the fast-moving flow when it's just a very narrow boundary layer. So here are some equivalent roughnesses. And this is this epsilon, sometimes called K sub S in some references, is the equivalent sand diameter, equivalent roughness. It's listed here both in terms of its SI units and traditional units. You can see that cast iron is relatively rough as far as new pipe materials go. It's rougher than galvanized iron, and wrought iron is even smoother still. Glass is a very, very smooth material. But a concrete pipe is really rough. A rough concrete pipe would have an equivalent sand roughness of 3 millimeters. That's the equivalent grain diameter of a roughened concrete pipe. So it seems sort of impossible that they used to make pipes out of wood. And we know they made barrels out of wood. If you've seen like an old Western movie or something like that, they always have barrels made out of wood. But they also used to make pipes out of wood. It was more economical to just have slats of wood and then try and wrap it with steel than making the entire pipe out of steel. They didn't have as much metal then, and it was much harder to work with metal. And so there are some places in Huntington that have clay pipes, vitrified clay, like brick, but I don't know if there's any place here in Huntington that has wood pipes. That would be interesting to see if there was. But remember, the roughness of the pipe material is one of the two things that affects the thickness of the boundary layer.
They use a glass drawn tubing, copper, what does that mean?
So glass is one pipe material that would have this roughness, and others would be like an extruded pipe. Like drawn means that it is, you know, those Play-Doh presses where they put Play-Doh in and you're squeezing it and it comes out extruded. So pipe materials that are extruded are usually much smoother than those that are like cast in place like concrete is. So drawn tubing just means it's something that was forced through an orifice. Yeah. Okay, so there's two things we're simultaneously putting together to tell us how thick is this boundary layer. Would anybody be willing to just put in their own words, what is the boundary layer? Who's the brave soul?
The area where the, I guess, laminar condition, but it's basically no matter how fast the water's moving, the flow's going to hit the laminar rate.
Right, exactly. So no matter how fast the water is going above it, there is a zone where, because there's not just one velocity in a pipe. Remember, there's lots of different velocities in a pipe. So it is how far away from the pipe you can go and conditions are still laminar. You know, above that, the Reynolds number is above 2,000 because the velocity is high, but there's some certain thickness. How far is that thickness where you can go and the velocity is still such that you have laminar conditions? That's the boundary layer that we're talking about.
So if like the velocity in the pump's just barely over turbulent, is that going to be a lot bigger?
That's right. Yeah, the boundary layer maybe would be the majority of the pipe. Yeah,
So does it change velocity?
it does. The thickness of the boundary layer changes with velocity.
So it's strictly the area where it went.
That's right.
So if I find myself like the dam,
Go to the laminar layer.
go to the laminar rate.
Exactly.
Is it all dependent on other stuff too?
It's dependent on the flow conditions and the pipe material. And so if you had like, think about if you had a really rough pipe, like a corrugated metal pipe, that's probably going to have a thicker boundary layer than a smooth pipe because the smooth pipe can't resist in the same way that a really thick, rough pipe can. Did you have?
Yeah, is there a boundary near the top of the pipe?
Yes, it's all the way around. And that's the difficult thing is that, remember, we're talking about something that's radial. And so it's not just really like the thickness in one-dimensional. It goes all the way around the pipe. So it looks like a donut, really. The boundary layer looks like a ring.
You go back to the pipe.
Go ahead.
The top here is the center.
Yes, the top here is the center of the pipe, precisely. Yes.
What's the dotted lines are boundary?
This dashed line here, or this dashed line, that dashed line is a different component of the figure. I couldn't crop it out. This dashed line means nothing.
So it's the thick one right there.
It's the thick one, right, yeah. Yeah.
So why do you have the shear stress for laminar above that?
Oh, okay, good question. So why, you mean why is the turbulent one above, or you mean why is it above here? Oh, okay. It's because even when the pipe is, okay, it's because the, how to put that? So you'd think if the conditions in the pipe are laminar, you'd think that the laminar is the entire zone of the pipe in general. That is because the equations we use to calculate the laminar layer aren't perfect. And this is the laminar layer thickness based on the empirical equations that I'm going to show you here in a minute. So I guess really the reason why it's not up to here, which is maybe what you'd expect, is it's an acknowledgement that the equations are just sort of a guideline. Yeah, that's not entirely satisfying because we want it to be perfect. It should be exactly the entire pipe. But let me show you the equations, and I think that'll make sense. Now, there's the two things that affect the laminar thickness. There's how rough the elements are and the flow conditions. And so let's say that we have, first of all, this empirical equation for calculating the thickness of that layer. It's called the Morris and Wiggert criteria. And it relies on the kinematic viscosity of the fluid, which is a property that varies with temperature and fluid. So water's is 1 × 10⁻⁶ meters squared per second at standard room temperature conditions. And then the shear velocity, remember we talked about that earlier, and you can calculate the shear velocity from the shear stress that's being applied from the pipe to the water, and also the density of the fluid. So this is just an empirical estimate of how thick that layer is going to be. It's not a perfect way of calculating it. Now, if you have this thickness, if you have the boundary layer thickness more than 1.7 times the roughness of the pipe, then you will say that you have a hydraulically smooth surface. Hydraulically smooth means that the laminar zone is thicker than the roughness elements in the pipe. But if that boundary layer thickness is less than 0.08 times the material roughness, then you'll say that you have a hydraulically rough surface. And so compare these two. In the one on top, you've got all the little mountains. That's, like the grains of the metal that the pipe is made out of, or if it's a concrete pipe, it might be the abrasive sand grains that give it that surface. So when you have a really thick laminar layer, and by thick what we mean is it's more than 1.7 times the height of these elements, then it's almost like these elements aren't even there. They're fully submerged in that laminar cushion. We'll have different flow conditions when conditions are hydraulically smooth compared to when they're hydraulically rough. Hydraulically rough means that the tips of those mountains, that the roughness elements project into the turbulent zone. These roughness elements don't get into the turbulent zone, and it's sort of like the turbulent zone doesn't really even know what's down there in the laminar zone. The laminar zone is shielding the flow from the roughness elements. But when the roughness elements project into the turbulent zone, then the flow conditions vary in a different way. We were looking at the Moody diagram in class last time, and that distinguishes hydraulically rough from hydraulically smooth. We'll go back to that Moody diagram in a minute.
Between the values.
What if it's between? And is there any gray area? There's a pretty huge gray area. If you look at that gap, less than 0.08 and more than 1.7. We call that transition zone. And we'll go back to the Moody diagram and take a look at what the implications of this are. So before we do this last example, let's go back to the Moody diagram. Again, this diagram is in your textbook if you want to find a nice big copy of it, but here is rough turbulent and transition, and here's the curve for smooth pipes. So the implication of it is that F value, once it gets past this dashed line, it's essentially horizontal. And so it means the Reynolds number once you increase the Reynolds number, it doesn't really affect the F value anymore. Once you get to the left of this dashed line, then it's not horizontal anymore. Once you get to the left of this dashed line, the Reynolds number is having an effect on the friction factor F. So rough turbulent zone, the F value is essentially a constant. So the thickness of this layer, what we're saying is, when it's hydraulically rough, once it gets into this zone, the F value doesn't change as a function of flow velocity because those peaks are already in the turbulent zone. But when we're in laminar conditions, when you have a very thick laminar zone, then if the flow gets a little bit faster, that's going to have a big impact on the F value. And so that's why that curve is coming downward, is that increasing velocity is making it more rough. Because if you increase the velocity, you're essentially making that boundary layer smaller and smaller, and those roughness elements are having more of an impact than they did earlier.
So it is peak, so it's just like theoretical, right?
Yeah.
Because
Yeah, I mean, think about,
you said the rougher it is, the bigger the laminar.
remember that artificially roughened pipe back in the lab? It's got like literally sand glued onto the inside of that steel pipe. That's an example of, these peaks don't probably look like regular mountain tops like this. I mean, they're probably more spherical in shape. But the second part of your question had to do with, right, and so if you're comparing the peak height rather than the flow conditions, if you had small roughness elements versus large roughness elements, then you're going to have more energy loss from the pipe that has larger roughness elements. And if you have more energy loss, the flow will be going slower, so you'll have a thicker laminar cushion.
Just looking at this, just it looks like the laminar on the top is bigger.
Yeah.
So laminar zone is bigger on the bottom one?
It depends on if the peaks are the same. I mean, there's two different things that are going on here. There may be different flow conditions, or it may be different roughness elements. What we don't know between the two of these, the main point of the illustration is just that the laminar zone here is down into, it's less than the peak height, yeah.
What you're saying is that the same velocity and flow conditions, if you have a rougher pipe, you're going to have a larger.
That's right, yeah. Same conditions, rougher pipe, larger laminar zone. Right. Okay, let's take a look at this example here. We have a water storage tank and a building on a hill, a high-rise building on a hill. There is a pipe connecting the tank and the building. The pipe is 250 meters long and 250 millimeters in diameter. And we know that from the water storage tank to the end of the pipeline, there's 16.4 meters of head loss. And we need there to be a pressure of 350 kPa in the building. So how tall should the tank be to make all of this true? And we're going to be applying the energy equation here. The tank height is the first thing we want to do. You can solve this first bullet point without knowing the F value, but then we can apply the Darcy-Weisbach equation here with the H sub F that's given and all the other pipe parameters. We can find, well, what was the F value for that condition? And then finally, we'll flip back to the slides before and take a look at a thickness of the boundary layer calculation. We'll go through that and find out what is according to the Morrison-Wigger criteria, what's the thickness of the boundary layer. So I'd like you to work together with a partner on this example, find how high is the water tank and what is the F value, and then together we'll do the third part of this example.
So we assume the H of head loss?
Head loss is given.
Oh, like
Yeah, in this case, we're not accounting for local losses. So what I told you last semester is H sub L has two components, H naught and HF. And here, the local losses are negligible. And so H sub L equals H sub F. Good question. All right, so get with the partner and solve those first two bullet points. All right, so let's take a look at where we're at so far. What's the water surface elevation required in the tank? Remember, it's the water elevation in that tank that is forcing the water through the pipeline and providing the pressure inside of the building. And what we know is that it needs a pressure of 350 kilopascals at the ground floor, meaning at the location where Z2 is 20 meters. So we set up the energy equation, and the tank is open to the atmosphere. In reality, it may have a roof over it. Here, it looks like it doesn't even. You know, there's birds flying over and all sorts of stuff going in there. But ordinarily, the tanks are open to the atmosphere. They're vented. They're not under positive pressure. So that's why we cancel out this first term, the pressure head term. The Z1, it remains unknown because we're finding how high the water needs to be in it. We cancel out the velocity head term at 1 because inside of the tank, the water is motionless. The water level isn't going up or down. They're pumping additional water up into the tank as needed. It'll fluctuate a little bit during the day, but we cancel out the velocity head term in the tank. P2 is that given 350 kPa divided by the unit weight of water. Z2 is the given elevation of 20 meters. And then the velocity head at 2 we leave in because that's the water velocity in the pipe. And so it does have, at location 2, there is some velocity head. Now, it's minor. The velocity head turns out to only be 0.846 meters. So it's relatively small compared to the amount of energy we're going to have to add in order to provide the pressure and to get it up the hill. The amount of energy we have to add to overcome the velocity head is small. And of course, we also account for the energy loss due to pipe friction. So in total, we have to have 72.924 meters of elevation. Z1, thank you. Yeah, Z1, I think I noticed that just now. So that's the elevation of the tank at 1. Any questions about that part? All right. Now, what's the name of this equation? Darcy-Weisbach equation, right. We want to rearrange the Darcy-Weisbach equation in order to find what's the friction factor that was coming into play here. If there was 16.4 meters of energy loss, then what was the F value that caused that? Well, we can put in the head loss, the diameter of the pipe, 2G, the length of the pipe, and the velocity, and find that that's an F value of 0.0194. So that was the F value that caused that. The way that we'd know directly that there's 16.4 meters of energy loss is, in reality, if you have an open tap and water's flowing out of that tap, then all of the energy that was in the water is lost when it comes out of the tap. If you know the elevation of the tap, it's obviously not pressurized once it comes out of the tap, and it's got a little bit of velocity head to it, but that's usually negligible. We'll have other problems where you'll know the amount of friction loss there was because you'll know the tank elevation that it came from, and you'll know the elevation where the water came out. So all of the energy that was there is lost to get it from one point to the other. So this third point, what is the thickness of the boundary layer according to the Morrison-Wiggert criteria? Let's give that a try. The first thing we're going to have to be able to calculate is what is the boundary shear stress. And to do that, we'll need to know the slope of the energy grade line. So what is the slope of the energy grade line? So S sub F is the variable we use for the slope of the energy grade line, and by definition, that is H sub F divided by L. How much energy was lost over the length of the pipe in question? Here we lost 16.4 meters of head over 250 meters of pipe. So the slope of the energy grade line is 0.656. That's the slope of the energy grade line. And we can calculate the boundary shear stress according to the equation, the unit weight, gamma, times the hydraulic radius r, times the slope of the energy grade line S sub f. What's the hydraulic radius for a circular pipe that's flowing full? D over 4. And that's what I did over here. When I calculated the hydraulic radius of the pipe, remember we did that proof last time where you can do area divided by wetted perimeter, and it's pi d squared divided by 4 divided by the wetted perimeter, which is pi d. And so that just leaves you with d divided by 4. So the unit weight of water, of course, is 9810 newtons per meter cubed. The hydraulic radius here is 0.0625 meters, and the slope of the energy grade line is 0.0656. That's the slope of the energy grade line. So the shear stress is 40.221 newtons per meter squared. So what that means is on the inside of the pipe, think about the area of the pipe. If you have 1 square meter of pipe area, that 1 square meter of pipe is pushing on the water, resisting flow, with a force of 40 newtons for every square meter of pipe area on the inside of the pipe. That's the shear stress. Okay, we can use that shear stress now to calculate the shear velocity. And that's one of the new formulas we looked at today. Shear velocity is equal to the boundary shear stress divided by the density of the fluid. And that is 40.221 divided by 1,000. That's kilograms per cubic meter. And that was newtons per meter squared. And we take the 1/2 power, and that is 0.200 meters per second. And so finally, the thickness of the layer, 11.6 times the kinematic viscosity divided by the shear velocity, and that means I'm late. I'm going to have to pay you back the extra 30 seconds I'm going to borrow from you today. 0.200 meters per second. So the thickness of that layer is 5.8 times 10 to the minus 5th meters. Or in other words, that is 0.058 millimeters. It's not very thick, but that's how thick the laminar layer is on the outside edge of the pipe. All right, so I'll see you next Tuesday. You've got a homework assignment due. Feel free to stop by during my office hours or anytime I'm in the office if you'd like some help or to check your answers on that assignment. I'd be more than happy to go over that with you. See you Tuesday.